Finally, now we're going to look at the specific application of the ideas of wickedness in climate science. So this article also came out recently. It's in 2013, and it's from the MIT Joint Program on the Science and Policy of Global Change. And they talk about very similar concepts without saying wicked specifically, or using the characteristics exactly as we've discussed them. But let's just see if you can see some of the similarities of these issues with the other wicked issues that we've been talking about. The big takeaway from this is that science could be part of the problem. So a simple issue of planning or the environment would be to remove human waste pollution from surface water. So this problem is caused by sewer outflow in urban areas. So clean up this outflow via treatment plants, and we'd have a solution. It's easy problem, easy solution. And any residual risk that we have, we know how to solve that also. So you can still boil your water, or you can bottle your water. So if we view our problem as waste in drinking water, we can build a wastewater treatment process. It's very linear, where we can come up with a solution. And if you look at there, that's basically a diagram. Wastewater comes in, clean water comes out. It's a very linear process. Climate change is a much more complex issue. And the article goes through all the variety of cycles and environmental aspects that are a part of it. But in brief, for example, you need to understand the effects of carbon cycle, how industrial gases interact with the environment, ocean circulation, which could be an 800-year process, and all of their associated feedback loops. So a simple image of climate change, exactly. So far, this just presents what the carbon cycle is. The carbon cycle is on the top portion of the screen. Talks about how much carbon dioxide gets into the air, which also depends on how much is in the soil, also depends how much is in the water, which also depends on how much is in fossil fuels that are produced, how much river runoff there is. You can see that there's a really wide, many number of ways that carbon dioxide can enter and leave the atmosphere at one point in time. And even more complex than this, as you can see, there's a deep ocean on the top. At the very bottom image talks about the deep ocean currents. So not only is there carbon dioxide in the water, we don't know where in the cycle, where in the world to look for the carbon dioxide. Not only that, what our big issue is climate change and heat. This is just all the many variety of processes that heat enters and exits the atmosphere. It's just an estimation from about 10 years ago about how much was being radiated in and radiated out. The specifics of this are not important. What's important to note is there's a lot going on, and for us to understand all of this, we need to be measuring all of these things accurately. So, for example, how science really impinges on policy. The scientific understanding of the planet contradicts the common mental models of environmental threat. So the wastewater treatment plant of a very linear process versus this whole environmental system behavior of a long-term change with a lot of noise. There was a lot of up and down arrows. We don't know which we're really measuring at which time. Additionally, even our thoughts are much more short-term. So we think in terms of the weather, whereas climate is the issue. You can hear, oh man, it's so cold. What happened to global warming? See, that's thinking linearly or locally for a global issue. Same thing with stocks and flows. If we were to stop releasing carbon dioxide right now, which would be stopping the flow, there could be a lot of stock built up in the ocean current or in any of those places that were in those diagrams that we need to figure out. Also, there's not just one source of climate change threat, but there's varied activities that contribute and are hard to measure. I think that diagram, if you keep on going back to it, shows it very well of which do we measure, which is the problem, which is not the problem. And how do we measure all of them at once? Because they really are throughout the economy, and many are even hidden. There's often talk of how cows are causing global warming, and that's because of cows release methane. How do we measure how much methane cows are releasing? Or even deforestation releases some methane, ice sheets melting. I mean, we can't set really up methane testing stations all over the world for this type of thing. So other issues of where the science really comes involved is that the reduction of threats requires emission mitigation by many nations, both rich and poor, creating an even more complex commons idea than ever before, the problem of the commons, where we have this common atmosphere. So rich nations really are able to reduce emissions. If you look at the statistics, they really haven't gone up much in recent years. But what about the nations that are more sensible to cost? So rising nations, India, China, Eastern Europe, Southeast Asia. If these countries want to industrialize, how do we enable them to do so without releasing emissions? And finally, the effects, or not finally, the next one, the effects of climate change at a local level are much more uncertain than the global scale. So globally, we can say temperature rises on average, 1 degree per every certain number of years. But locally, things are changing much more drastically, such as changes in precipitation, changes in hurricane rates, changes in rainfall. So, but how do we convince then, or how do we discuss where the local level problems are really resulting of global issues, but it's localities that need to make the adaptations? And again, this is you can see the great number of complexities that go into this. And finally, there's uncertainty in scientific analysis of the response, and therefore it complicates the process of what do we do? What do we do to stop this? And this comes in if you remember your high school or college chemistry or physics classes. There's always some error in measurements. When all these errors for all these processes are combined, how do we know which to use? How do we know if it's even true anymore? What if Greenland or Antarctica, one of their glaciers, just collapses all of a sudden? What's going to happen to our models then? And because of all this uncertainty, unfortunately, some people believe that it's just a belief in climate change. And that is perfectly acceptable if you just take all this uncertainty to mean that it might not actually be going on. So as a takeaway from this article, you should really see that science, while doesn't provide the answers, might also actually be producing more problems than if we try to interpret actual natural science for these larger issues. And what we need to do, we need to address the planning issue of climate change using language similar to that of wicked problems. We can't think of it linearly as science of how can we measure, how can we stop, when there's so many processes going on that are interconnected. We really need to figure out where's the best place to intervene in this larger cycle. Thank you, and enjoy your readings.